particle of mass 0.8 kilograms is moving in a straight line on a rough horizontal plane. The speed of the particle is reduced from 15 to 10 as the particle moves 20 meters. So assuming the only resistance to motion is the friction between the particle and the plane, find in part A the work done by the friction in reducing the speed of the particle from 15 meters per second to 10 meters per second. Okay, so this is just an energy problem. Okay, you can see here it's lost energy, hasn't it? Because it's traveling here with a much faster speed than it is 20 meters later. Okay, so we can measure the energy that's been lost. Okay, and the energy that's been lost then is been lost due to the work that's been done by the friction. Okay, so we can write that as a statement, can't we? We could say, look, the work done by the friction, quite simply, is the change in energy, right? Or the loss in energy even. Now what energy here have we lost? Well, we're losing speed, aren't we? Okay, so it's lost kinetic energy. So the change in kinetic energy is what we're interested in. Okay, there's no potential energy changed here, okay, because it's all on the horizontal, okay, horizontal plane. So there's no vertical movement, so we don't have to worry about gravity, okay, the effect of gravity on energy in this case. Okay, so we're just interested in the change in kinetic energy. Well, remember the formula for kinetic energy. Okay, so kinetic energy is half times the mass times the velocity squared. Okay, so we'll see what the change is. Well, we started with this speed here, didn't we? So it'll be half times the mass, which is 0.8, times that speed, which is 15. Okay, and you've got to square that speed, of course, right? So that's what the kinetic energy we had to begin with. Well, we work out what kinetic energy we had at the end, and then we'll see the difference. Okay, so we need to take them away to work out what that difference is. Okay, so we get our calculator. So let's work out the energy at the beginning. So we got 90 joules of energy there at the beginning, and at the end we had 40 joules of energy. So it's lost 50 joules of energy. Okay, kinetic energy there. Okay, due to the speed loss in speed. So the work that's been done by friction, okay, is 50 joules. Okay, that's the work that's been performed there to slow this particle down. Okay, so then in B, all right, it says the coefficient of friction. So we've got to find the coefficient of friction between the particle and the plane. Now before we do that, okay, we need to sort of use this answer here and appreciate, okay, if the work done by friction, okay, is 50 joules, well, of course, we've got a formula for work done, haven't we? If you remember, the formula for work done is force times the distance that it's applied for, yeah? That's how you work out work done, the force that's applied multiplied by the distance that is applied for. Now, the force in this case is friction. So you can call it F, some people, you know, for friction. I like to call it FR there, little r, so I know it's my friction there. And I'm going to multiply it then by the distance, okay? So, of course, the distance is travelled was 20 meters, okay? Equals then to 50 joules, the work done. And from there, then you can actually work out what the frictional force is, okay? So, obviously, you take that 20 over and you divide. So, 50 divided by 20 then will be 2.5, okay? And because it's a force, it's going to be measured, of course, in newtons. There's a 2.5 newtons. So that's what the frictional force is. Now that we know the frictional force, okay, we can then easily work out what the coefficient of friction is. So that brings in sort of year 13 work here in terms of friction work, but it's easily done. Okay. What you find helpful with this though is if you draw a force diagram, okay, to help us work out what the coefficient of friction is. Now with a force diagram, we focus on the actual object, okay, and we'll look at the forces here that are affecting the object. Okay, so now if you think about it, the object is sitting on the ground, isn't it? Okay, so the weight of the object pushing the object down onto the ground, which was obviously mass here, which is 0.8 kilograms times gravity. So that's the weight of it. But remember then, okay, the object doesn't sort of fall through the ground, it stays there, so there must be a force pushing it up, and that will be the reaction, okay, the normal reaction of the ground pushing up so that the object stays in place. The other force acting, of course, was the friction, okay. Now, when the friction is at its max, okay, right, we've got a formula for it, okay. So when friction is at its maximum value, the friction, Fr, will equal to, so friction will equal to mu R, okay, where mu is the coefficient of friction, of course, okay. So mu is the coefficient of friction. Now, it will be at its max, the friction will be, okay, because it's moving. Friction will be at its max, then it can't be any more. So what you do now is, okay, you just plug into the formula what we know. Well, we know the friction is 2.5, okay. We want to work out what mu is. The question is then, what is R? Well, R is, remember, the normal reaction. And for this to stay on the surface balanced, the reaction has to match the weight there. So these have to be equal. So the reaction will be 0.8 G. Okay. So from here, we'll work out what this is, because G, of course, is 9.8. And then your mu will be the 2.5 divided by whatever this is. Okay. So 0.8 times 9.8 will be 7.84. So you get that from mu there. So let's type that into the calculator to see what we get out. What that comes to be. Okay, so it's not particularly nice. We can write it as a fraction, 125 over 392. Okay, and we found there the coefficient of friction.